Hello all, my name is Kari Kivelä and I'm studying in the Metropolia University of Applied Sciences in Helsinki. Computer engineering, major is in embedded software, and this is my thesis. It's about the design process of an open source mobile phone. So let's start. So, well, I wanted to make a GSM phone with an embedded CPU based on open source. Would be hobbyist friendly, easy to hand solder, and could make calls. So overview. First, choosing the main chipset, covering PCB design, going over software and also the application that controls the hardware. Proof of concept, what results and what improvements found out. So first of all, let's go over hardware development kits. Anytime when developing a device, it's very good to know chipset manufacturers. They usually give a reference platform that they have tested, has all the features open, exposed for easily evaluating different features. So that, for instance, you can easily access the USB, maybe USB, you can put USB devices, easily connect USB device, GPIOs are exposed, different kind of buses are exposed, that maybe in a CPU that has many peripherals. So no need to spend time designing cumbersome analog circuits, but it just works. It allows you to rapidly start development. And prototyping, and also it helps debugging because let's say that you have a device ready and your own custom device and it doesn't work, so you can go back to the reference platform and see what worked there, what didn't work. You can compare the scenarios. So I took for CPU, I took Freescale ARM processor, LQFP package so that it's easily hand solderable. That's MMU so it can run Linux. Here it is. This is the processor, and here is the hardware development kit for it. You have the USB slot here, GPIOs. For GSM, I chose SIM 900. It's a quite widely available chip that is used by a hobbyist. Hobbyists, it can make calls, SMSs, cellular data, but this project only covers the calls, and controlled by 80 commands over UART. Here is a diagram of the UART. These handshake signals are not used actually in this project, and they're not needed. And this one is also hand solderable, like it can be seen here. Fairly easily hand solderable. At least I can solder that. So hardware design, made the PCB with KiCad open source software. Made the logical design with the components and their connections between the pins of the components, which I then kind of exported into the layout design, which means I had to put them, place them in the layout and place the traces between them. A lot of work. For this proof of concept, the keypad is only a button and the screen is an LED light. And here is the final PCB part of it. So you can see both layers. It's two-layer design, both layers, some traces here, vias, so on so forth. Software design, wanted to be open source, went with embedded Linux. I covered in my work compilation of kernel. Nothing really special there. Just wanted to make it part of the project. Compiled it and cross-compiled it on x86 for ARM. User image rootfs with all the software and especially with Python support. I'll get into the Python in the next slides, but it was Python was controlling hardware, and I use Git for source control of the hardware design and of the Python code. So the Python scripts they start after during the operating system init automatically. They control GPIO and UART. GPIO for button and for the screen and for the keypad, and UART for the modem. Through operating system file system handles, yeah. That you can just write to and read from, and this is how you access, and then easily you can on Python intuitively write your logic application. And I wrote an 80 command parser and constructor, and polling for the keypad, sending commands for the modem, and also reading commands from the modem and notifying the screen. The proof of concept, it's like demonstrating an idea you have, a concept you have, without having a fully featured complex product. So it's just something that is enough to show that what you aim to do is working, and maybe it's not fully functional, but it shows that the device has the ability and the potential to work well. So let's start by going over the proof of concept device. So everything is in a box. There is the development kit for the GSM, for the CPU. They are both externally powered with the separate power supplies. Debug UART for the CPU, then screen, keypad, and let's start by making a phone call. I will power on first the GSM module. Okay, now there is light, and in the reference platform you must boot it with a separate button. So let's do that. Get some more lights. Starting to look for network. Okay, now it found it. Let's power on the CPU. Oh, kernel panic. Let's try again. Looking at the debug UART side. Looks much better. Once the Python script starts in the init, it should be notified on the screen. And here we see the LED is lit. It's blinking a few times. After that, the Python has has finished the init sequence, and now we should be able to make a phone call. So I will initiate a call by pressing the button, and what we should see is that the LED is lit to notify that call is underway. So let's try. Okay, looks good so far. Let's see. It has a pre-programmed my cell phone number. So let's try the answer. There's no microphone connected, so we can't hear anything. But there it is, connected. Now ended the call. Because this is still in a proof of concept stage, so I need to reset both devices before the next operation. So I will turn off the power for both devices, and we'll then we will then go on to answering a call. So let's turn on the power again for the GSM. No, not that slow. That's okay. Again, the same thing. Pressing the button. It found the network. Let's turn on the CPU. And based on the debug UART, it looks like we're booting up. We'll see soon from the screen of the phone what is happening. Yeah, the LED is coming up again, blinking. Okay, that's it. Should be now initialized. Now let's try the call. I've had some issues with answering, so let's hope it will work. But what we should see is that the LED will light up, will be lit up, showing that there is an incoming call. So let's do that. Let's press call. Hopefully this is not too far, not too close. Putting speaker on. See, oh, here is the LED. Let's hope we can answer. Oh, well, this time it actually worked, but this is also one thing that now it's calling us back. It's because of the, but we still have the, so it looks like we were put on hold by the GSM modem. So there are still stuff on the Python infrastructure that needs to be done, but it can be seen that that it works. It's a proof of concept. So if I would now go to Samsung and show this to them, they would be very satisfied, seeing that this phone works, right? So I'll disconnect this call, and I will also power off our device. And I will continue with the presentation. So then getting into results, so we can definitely see that the embedded system works, CPU works, peripherals work. I get the Linux, embedded Linux up on it. I can access GPIO on UART. I can access the modem. And I'm also able to make calls, able to kind of answer calls, but as you could see, it's same time we go to the next point that the Python infrastructure requires more work, because like you could see, I at the same time answered the call and then started making a call. Also, the PCB can't be printed. I made a mistake with the rules, and the printing house, it's too small for them to print it. So improvements, need to develop the Python further, make a real keypad with button for each number and calling, and a button for calling and rejecting a call, and also making a real screen that will show at least the incoming phone number and having some kind of status as text. What is the status of the phone? And need to go over the PCB design, if we can make it better so that it can be printed. And also next stage is to use battery power for the device. So any questions? If not, so we'll end this presentation. Thanks a lot for watching.